Thursday, since I will not be around this Thursday whole day. So, but practical class will resume as usual. Okay. Mr. Shahir helped me to take over the class. Okay, together with lab officers. Okay, Mr. Cyril and also Mr. Raimi and Mr. Zuhair. Okay. Since we don't have much time left, so this week would be the last week for my part for the first half. So I'm going to see you for the last time this Friday. Still, we do have class this Friday before we end up the first 7 weeks of the semester. Okay. All right. We will not have any lecture on Thursday morning, but the lab practical will resume as usual. Okay, so for today, even though we should have 2 hours, I'm trying to cover up to cover as much as I can for this 1 hour. Still, we do have another 1 hour for on the Friday, so that maybe we can finish up or you can ask anything related to the topics that we have discussed on Friday. Okay, and also on Friday, I'm going to discuss with you on your SCL activity. Okay, yang tu kita tunggu nantilah Jumaat baru kita discuss on your assignment for SCL. Okay, okay, 41, not bad. Okay, good numbers. Okay, so for today, we are going to proceed with cholesterol biosynthesis. Can you see the screen? You nampak slide tak?
Yes, Doctor.
Okay, all right, okay. So on cholesterol biosynthesis. So from fatty acid oxidation, from fatty acid biosynthesis, on the biosynthesis of triacylglycerol, on other lipids. So now, okay, we will going to discuss on the cholesterol biosynthesis. Okay, so we know that cholesterol. We have been one thing that we know about cholesterol is the position, okay, of cholesterol in, okay, can lead to this one, okay, can lead to cardiovascular disease, okay, and also stroke, okay, something that are very common that are related to cholesterol. So cardiovascular disease and also strokes are the 2 major causes of death in humans. Okay, these are the 2 leading causes. Okay, leading causes of death in humans. Okay, but cholesterol is a very important, is a vital constituent of cell membrane. Okay, is part of the cell membrane. So now, one thing that you, okay, even though I'm not going to cover on the membrane cell, but you should now try to look how does this cholesterol plays a very important role in the formation of the cell membrane. So what is the role of cholesterol in the cell membrane? Okay, in the function of membranes. Okay, we know that cell membrane helps to, okay, it helps to hold different components. Okay, it helps to hold different components, okay, of the cell together. Okay, and also plays a very important role to protect, okay, to protect it from the environment outside the cell. Okay, we know that cell membrane also regulates, okay, what coming in, what coming out, what enters and what exits from the cell. Okay, so that our body, okay, will not lose, okay, too much, okay, too many nutrients, or our body will not take in too many iron, for example. So it regulates what enter and also what exit from the cell. Okay, so how, okay, what is the important role of cholesterol in cell membrane? So you know that cell membrane has this lipid bilayer. Okay, lipid bilayer. Okay, lipid bilayer. So what are the components in that form this lipid bilayer? So one of it has this phospholipid. So cholesterol is randomly distributed, okay, across the lipid bilayer. So the role of the cholesterol, it helps to maintain the lipid bilayer in a fluid environment, okay, to stay fluid, okay, in whatever environment. Okay, also it helps to hold the lipid bilayer together, because without cholesterol, phospholipid will start to separate from each other. So try to look on the structure of membrane cell, membrane cells, so that you can see the importance of cholesterol. So it helps to hold, okay, the phospholipid, to hold the lipid bilayer. Without cholesterol, the phospholipid will separate, okay, from each other. Okay, so it's present in tissues and in plasma either as free cholesterol or as storage form. Okay, so we know this. Okay, in plasma, either free cholesterol or a storage form is transported, okay, through lipoprotein. Okay, so plasma LDL is the vehicle of uptake cholesterol and also cholesterol ester into many tissues. All right, okay, so what are the sources of cholesterol? Okay, so in our body we have this, okay, cholesterol pool. Okay, so liver is the main organ, okay, the important organ, okay, in the cholesterol synthesis. Okay, so where does it go? Everything will go to liver. So we can, okay, the sources of cholesterol, obviously it comes from diet, okay, from the de novo synthesis, and also the one that's synthesized in the extrahepatic tissue. So basically, so in general, we can say that liver hepatic cells is the most the important organ that related to cholesterol synthesis. Okay, so once we do have all these sources of cholesterol, so cholesterol in the liver can be secreted out, okay, as HDL and also the LDL. It also can be secreted in a free form, okay, which is free cholesterol, okay, or in bile acids. Okay, it also can be converted to bile salts and or bile acids. So we are going to discuss on the mechanism of the conversion of cholesterol to bile salts, okay, or bile acids, okay, later at the end of the topic. Okay, so this is the structure of cholesterol, okay, something that you need to know, okay, on the structure of cholesterol. Okay, so if you look at the structure, if you come across these 4 hydrocarbon ring, okay, so basically this is a structure of cholesterol or its derivative. Okay, it has this 4 hydrocarbon ring. Okay, if you, okay, from this diagram, we okay, you can conclude, okay, you can do your own summary. So basically, cholesterol, it has 4 hydrocarbon ring, it has 27 carbon, okay, it has this hydrocarbon tail, it has hydroxyl group, okay, still have hydroxyl group, okay, and also it has this methyl group, okay, at carbon 10 and also carbon 13, okay. All right, so all steroids, okay, have this structure, okay, all steroids, cholesterol, okay, steroid is derivative of cholesterol. So they have this structure that known as cyclopentanoperhydrophenanthrene ring, okay, and one thing that makes the structure of cholesterol unique is all carbon atoms of cholesterol are derived from acetyl-CoA, okay, from acetyl-CoA or acetate. Okay, and this statement has been discovered, okay, through experiment by I think German scientist, if I'm not mistaken, Konrad Bloch. Okay, Konrad Bloch, that from the experiment, they discovered that all carbon atoms of cholesterol are derived from acetyl-CoA or acetate. Okay, so all right. So this is like how you summarize the structure. What does it have in the structure of cholesterol? So it has hydroxyl group at carbon 3. Okay, it has double bond between carbon 5 and carbon 6. Okay, it has 8-membered hydrocarbon chain. So this is the hydrocarbon chain, okay, at carbon 17. And also it has methyl groups at carbon 10 and also carbon 13. Okay, and you also should know from, okay, the location of the first numbered, how they numbered, okay, the structure of cholesterol. So this is carbon 1, 2, 3, 4, 5, 6, 7, 8, okay. Okay, and okay, so you should know this hydroxyl group at carbon 3. Okay. All right. So now let's move to the biosynthesis of cholesterol. Okay, so the pathway, okay, it occurs in the cytosol. Okay, it occurs in cytosol. Okay, so it has this NADPH that involved in the reduction reaction. Okay, that supply the reducing equivalents. Okay, there are steps that require ATP. Okay, okay, and the all carbon atoms are provided by acetyl-CoA. Okay, and liver is the most active organ that involved in the biosynthesis of cholesterol. Okay. All right. So now let's move to the biosynthesis pathway of cholesterol. Okay. For production of one molecule of cholesterol, it requires 18 molecules of acetyl-CoA, 36 molecules of ATP, and 16 molecules of NADPH. So in the formation of one molecule of cholesterol, so these are how many moles of acetyl-CoA, ATP, and NADPH required, okay, in the reaction of forming one molecule of cholesterol. So I would like to divide the biosynthesis of cholesterol into these 5 stages, 5 steps. Okay, there are textbooks like to shorten into 3. There are depends. Okay, but this is how I would like to differentiate between stages. Okay, first involved is the synthesis of mevalonate from acetyl-CoA. The second one is the formation of isoprenoid units. Okay, third step, formation of squalene. Okay, fourth step is the formation of lanosterol. Then from lanosterol, it forms cholesterol. Okay, so there are 5 stages involved in the biosynthesis of cholesterol. Okay, so Okay, let's discuss on the first step, okay, in the formation of mevalonate. Okay, so this is how mevalonate is synthesized from acetyl-CoA. So now acetyl-CoA is the precursor, the starting molecule involved in the biosynthesis of cholesterol. Okay, if you look, okay, in the formation of mevalonate, there is an intermediate that called as a HMG-CoA. Do you still remember HMG-CoA? We have discussed. Okay, so HMG-CoA involved in what pathway?
Lipid.
Lipid mana? Which lipid? Which pathway that involve the formation of HMG-CoA? Give me 5 minutes kejap. Kat mana?
Ketogenesis.
Ketogenesis in the formation of ketone bodies. So can somebody describe on the ketone bodies what? So now we have, okay, what are the difference that you think that made that explain the difference of HMG-CoA production between ketogenesis and also cholesterol biosynthesis. Ketone bodies formation berlaku dekat mana?
Mitochondria.
Okay, mitochondria. So this one, it occurs in Adila. Okay, you all okay?
Yeah. Okay.
All right. Okay. Second screen share balik. All right. Okay. All right. So in the formation of mevalonate, so it involves the production of HMG-CoA. So what happened in the formation of mevalonate? So basically, it involves 3 molecules of acetyl-CoA, which the first reaction involves condensation. Okay, condensation reaction between 2 acetyl-CoA to form acetyl-CoA, and this reaction catalyzed by thiolase. Okay, condensation reaction between 2 molecules of acetyl-CoA forming acetyl CoA through thiolase reaction. Okay, and the second step, okay, involve another condensation reaction between acetyl-CoA with another acetyl-CoA, and this reaction catalyzed by HMG-CoA synthase, okay, and produce this HMG-CoA. So this is a cytosolic HMG-CoA produced in cholesterol biosynthesis. All right, then HMG-CoA is reduced to mevalonate by an ADPH dependent reaction, okay, by HMG-CoA reductase. Okay, so this is the enzyme that catalyze the conversion of HMG-CoA to mevalonate. Okay, so this HMG-CoA reductase enzyme, it is a very important enzyme. So this is a rate limiting enzyme that involved in the regulation of cholesterol biosynthesis. So this enzyme, so this step is where, okay, that has been utilized in medical system they have designed a drug, okay, to replace, okay, this HMG-CoA reductase that have been used in medical to help to lower down the cholesterol in our body. For those who have problem with cholesterol, so doctor will prescribe you drugs like statins, okay, like simvastatin. There are different drugs that mimics, okay, that mimics the HMG-CoA reductase, because this enzyme is the rate limiting enzyme in cholesterol biosynthesis. It involved in the regulation, okay. So okay, drugs that have been designed, okay, according to the HMG-CoA reductase reactions. Okay, now we have this mevalonate. So the first steps, okay, the first stage involves the formation of mevalonate. Okay, so okay, we have discussed on this. Okay, then okay, next step is the formation of isoprenoid unit from mevalonate. Okay, isoprenoid unit of mevalonate. So from mevalonate, now we are going to produce this isoprenoid unit, which is isopentenyl pyrophosphate. Okay, isopentenyl pyrophosphate. So if you look at the structure, okay, of this from acetyl-CoA, okay, it undergo condensation to form acetyl-CoA. All right, then okay, then it undergo another condensation reaction to form HMG-CoA. All right. Okay, so now before it reduce to mevalonate. So this is, okay, from mevalonate, okay, if you look at the structure, this is now we have this hydroxyl group. Daripada acetyl-CoA, we know that acetyl-CoA doesn't have this hydroxyl group. But after the reduction of HMG-CoA, because it's an ADPH dependent reaction, now mevalonate, okay, has this hydroxyl group structure. Because this hydroxyl group is has important function in the formation of isoprenoid unit. Okay, so this new hydroxyl group that has been formed during the formation of mevalonate, okay, during the formation of mevalonate is going to be phosphorylated. Okay, is going to be phosphorylated by this enzyme, mevalonate 5-phosphotransferase. Okay, so now we have this 5-phosphomevalonate. From mevalonate, it undergo phosphorylation. Okay, now we have this 5-phosphomevalonate. Okay, so this 5-phosphomevalonate undergo the second ATP dependent ATP dependent another phosphorylation to form this pyrophosphomethylonate. So this is the enzyme that catalyzes the second phosphorylation reaction, which is phosphomethylonate kinase. Okay. All right. So the third one is the conversion of 5-pyrophosphomethylonate. So this reaction is catalyzed by pyrophosphomethylonate decarboxylase. So basically the third step is an ATP dependent decarboxylation, and it produces this isopentenyl pyrophosphate. So we can conclude that in the formation, in the production of isoprenoid unit, it undergo 3 phosphorylation steps and 1 decarboxylation step to produce this isopentenyl pyrophosphate. Okay, so phosphorylation occurs at the new hydroxyl group, okay, in the methylonate structure. Okay, so isopentenyl pyrophosphate, it can undergo isomerization to form this dimethyl allyl pyrophosphate. So it undergo isomerization. You can see the difference between the structure. Okay, at which carbon does it isomerize? Okay, so between IPP and also the MPP. Okay, isopentenyl pyrophosphate and also dimethyl allyl pyrophosphate. So these two molecules also known as activated isoprene. Okay, so you should know what is isoprene. Okay, isoprenoid is isopentenyl pyrophosphate. Okay.
Doctor,
Yes.
so from methylonate, it undergoes 2-time phosphorylation and then 2-time decarboxylation.
Okay, the first 2 steps is it only involve phosphorylation. Okay, decarboxylation occurs hanya only at this stage, only at the 3rd phosphorylation. Okay, the first and second it only involve phosphorylation, but at the third phosphorylation it involves decarboxylation too. So the third step too, they involve both phosphorylation and also decarboxylation.
The second one, what reaction is that?
Okay, the first reaction involves phosphorylation, okay, at this hydroxyl group. So now you have the addition of phosphate group, okay, replace this hydroxyl group, okay, nampak tak? Okay, so now we have this phosphomethylonate. Okay, the second phosphorylation, another phosphorylation, okay, either the name of the enzyme phosphotransferase, meaning that it transfers phosphate group. Okay, the second enzyme, okay, the second enzyme is kinase. Okay, kinase, it also tells you that it helps to transfer phosphate group. Sama, kinase or phosphotransferase is all about the transfer of phosphate group. Okay, so the second step is phosphorylation. So it adds another phosphate group from ATP, okay, to this phosphomethylonate. So ditambah lagi satu phosphate group. So now we have this pyrophosphomethylonate. Okay, kalau pyrophosphate is it consists of 2 phosphate group. Okay, from 1 phosphate group in phosphomethylonate. So now we have 2 because it undergo 2 times phosphorylation reaction. Okay, dah 2 kan phosphorylation. Okay, from pyrophosphate methylonate, it undergo another phosphorylation, but this time it also involves decarboxylation. Okay, in this diagram, dia tunjuk satu-satu. Okay, it shows one step followed by another step. So it shows the first phosphorylation. Okay, it shows, okay, it undergo the 3rd phosphorylation. So ditambah dekat sini. Okay, the third phosphorylation, the third phosphate group is added here, but then it undergo decarboxylation, which it removes one carbon as the carbon dioxide, and also it removes this phosphate group. Okay, so now it produces this isopentenyl pyrophosphate. Okay, Fatia?
Okay, faham, Doctor. Thank you.
All right, okay. So isopentenyl pyrophosphate can undergo isomerization to form this dimethyl allyl pyrophosphate. Okay, you can see, okay, at which carbon, kat mana, okay, berlakunya this isomerization. Okay. All right. So now from isoprenoid units, now we want to synthesis squalene. Okay, part ni interesting. Okay, saya suka sebab nama dia macam menarik. Okay, so now we have this IPP and also DPP, isopentenyl pyrophosphate and dimethyl allyl pyrophosphate. Okay, so now both are 5 carbon. Okay, isopentenyl you can isomerize to dimethyl allyl pyrophosphate. Both are 5 carbon components. All right, so in the synthesis, okay, in this pathway, okay, to synthesis squalene, in the formation of squalene, so it involves 3 reactions, okay, with 2 enzymes, okay. The first, okay, one is perennial transferase enzyme, and also another one is squalene synthase. Okay, now, first reaction, now kita dah ada, okay, we have both this isopentenyl pyrophosphate, okay, and also dimethyl allyl pyrophosphate daripada sini. Okay, we have these both now. Okay, in order to produce squalene, so these two, DMPP and IPP, saya short form, okay, it undergo condensation. Okay, it undergo condensation. So perennial transferase enzyme catalyze the head to tail condensation between dimethyl allyl pyrophosphate and also isopentenyl pyrophosphate. So this enzyme and this reaction involves the removal of pyrophosphate. Okay, so it produces this geranyl pyrophosphate. So do you understand what does it mean by head to tail condensation? Okay, we have both. Okay, in this structure, basically now we have both. Okay, kita ada head and also kita ada tail. So you should identify which one is head, which one is tail. Okay, maybe dekat DMPP dia berlakunya reaction dekat head and it react with the tail of isopentenyl pyrophosphate, and it involves the removal of pyrophosphate. Dia akan remove this pyrophosphate either from I'm not really sure, but either is it these 2 pyrophosphate, is it from either from isopentenyl or from dimethyl allyl pyrophosphate. Okay, this condensation between these 2 molecules produce geranyl pyrophosphate. Okay, so from 5 plus 5, now we have this 10 carbon geranyl pyrophosphate. Okay, all right. So geranyl pyrophosphate undergo another head to tail condensation with isopentenyl pyrophosphate and catalyzed by perennial transferase, the same enzyme, the similar enzyme, okay, to produce this farnesyl pyrophosphate. Okay, from geranyl to farnesyl. So from 10, we add another 5. Now we have this 15 carbon farnesyl pyrophosphate. Okay, another head to tail condensation. So it removes 2 molecule of phosphate group. Okay, pyrophosphate. phosphate to produce this farnesyl pyrophosphate. Okay. All right. So farnesyl pyrophosphate now. Okay. So basically, in this reaction, it involves it can be explained through a mechanism, okay, which is SN1 mechanism. Okay, it involves the formation of carbocation. Okay, so but I think I'm not going to discuss on the SN1 mechanism. If you have time, try to find, okay, try to search of the SN1 mechanism in the formation of farnesyl pyrophosphate. Okay, so how this the formation of carbocation, how this phosphate group attacks, okay, that form carbocation, then how the reactions helps to produce farnesyl pyrophosphate. Okay. All right, so now we have this farnesyl pyrophosphate, okay, 15 carbon molecule. Now it undergo head-to-head, okay, tadi head to tail kan, head-to-head reaction, okay, and this reaction catalyzed by squalene synthase. It involves, okay, NADPH, okay, so head-to-head reaction, head-to-head fusion between two farnesyl pyrophosphate to form squalene. So 15 dengan 15 jadi 30 carbon molecule, which is squalene. Okay? You all okay ke?
Okay, ko.
Okay, Doktor.
Okay, okay, from mevalonate, okay, from acetyl-CoA, we get this mevalonate. From mevalonate to isoprene unit. From isoprene unit, we have this squalene. Okay, so you should identify what are the intermediate, okay, in the cholesterol biosynthesis in sequence. Okay, daripada acetyl-CoA, mevalonate, isoprene unit, then we have this squalene. Okay, squalene dah 30 30 molecule, 30 carbon. So still squalene is a linear hydrocarbon. Dia belum cyclic lagi. Okay. So now the next reactions, okay, is to form it's going to cyclize, okay, to form tetracycline. Okay, there are two enzymes, okay, involved in the conversion of squalene to lanosterol. Okay. Okay, first enzyme is squalene monooxygenase. Okay, and also the second one is cyclase. Okay. Okay, so squalene is undergo reaction that catalyzed by squalene monooxygenase, and this reaction use NADPH as a coenzyme, and it require oxygen as well. Sebab tu nama dia monooxygenase. So squalene now produce squalene 2,3 epoxide. Okay, squalene epoxide. Okay, so from squalene 2,3 epoxide, it undergo another 2 steps, okay, to form this lanosterol. So basically, this reaction at this stage, okay, especially in the formation of lanosterol to cholesterol, basically kat sini dia tulis many reactions kan. So the certain book state that it involves another 19 steps. It's a very complicated steps, okay, that involve in the formation of cholesterol. So from squalene, okay, we produce lanosterol, then lanosterol, okay, we can produce cholesterol. So cyclization reactions form lanosterol. We can see that the first one, the first molecule that have a complete cyclic structure is lanosrol. Okay. All right. Okay. So this book by Freeman and Company, okay, it said that from lanosrol, so it requires another 19 steps, okay, to form cholesterol. Okay, so okay, from squalene to triepoxide, it can undergo different reaction to produce different derivative of cholesterol, like sigmasterol, ergosterol, okay, like in plants. Okay, I'm sure kalau for those who take plant biochemistry, I'm sure you heard this. Okay, sigmasterol is a component, okay, that is a component that produced by plant. In fungi, it produces ergosterol, okay, and all this we have this kalau in animal we have the cyclase enzyme, okay, to produce lanosrol and also cholesterol. Okay, so I hope you can go through go back to the biosynthesis, the pathway of cholesterol biosynthesis from acetyl-CoA to cholesterol. Okay, so these are the equation, okay, for the complete biosynthesis of cholesterol from acetyl-CoA. Okay, I got this from one of the textbooks, okay, because we don't really understand what happened, okay, in the formation of cholesterol from lanosterol. Okay. Okay. I hope you have some idea on the cholesterol biosynthesis in the okay pathway of cholesterol tadi. Okay, so on the regulation part of cholesterol synthesis, regulation is very important. Okay, we know that regulation is very important. So basically, we need to have a very balanced, okay, either balance in terms of sugar in our body, in terms of cholesterol, because all this is maintained, okay, is maintained between is maintained between the biosynthesis, between the utilization, also in terms of transport of cholesterol. So we need to have this regulation, okay. In fact, in glycolysis pun ada regulation. So which enzyme, rate limiting enzyme. Okay, we know that in cholesterol biosynthesis, HMG-CoA reductase is the key, is the rate limiting enzyme. Okay, so that's the location where all these regulation occurs. So that's the location where the scientists design drug, okay, to help in the lower down the cholesterol level in for those who experience this lipidemia, okay, cholesterolemia, okay. Okay, I'm sure, okay, you are still young, okay, but make sure you control your cholesterol, your fat intake, okay, in your diet, so that you will not have problem with cholesterol, because cholesterol, okay, high cholesterol in your body you cannot detect. Okay, sometimes nobody know that you have a very high cholesterol level in your body, except if you are doing blood test, you are doing your medical the whole medical test kan, buat blood test and everything. Okay, we don't want you, at least if you have if you have that opportunity, go and do medical checkup. All right, check your blood sugar level, your cholesterol level, so that if we know early, so that we can, so doctor can prescribe you with with medical prescription, okay, drugs to help in control to lower down your cholesterol level. Otherwise, at the end of the day, you are already in the last stage, it's already affect, okay, your kidney, your liver, it will affect your heart as well. So we don't want that. Okay, sometimes other people yang dah last minute, okay, so baru tahu bila ada problem with your you short breath ke, you ada problem with okay, macam-macam, baru tahu bahawa you punya cholesterol level in your blood is very, very high. So we don't want that, okay. You are still young, monitor your intake, have a very good diet, okay. Okay, now as early as 30 pun ramai yang dah makan ubat high blood pressure, dah makan ubat cholesterol. So remember that, okay. All right, so these are the mechanisms, okay, involved for the regulation of cholesterol synthesis: competitive inhibition, feedback inhibition, covalent modification, steroid-mediated regulation of transcription. Okay, so there are many, there are 4 different mechanisms to explain on the regulation of cholesterol synthesis. Okay, either we can regulate through drugs, through feedback, through the intermediate itself, through hormones, okay, and also through at the transcription level. Okay, what is competitive inhibition? Okay, so there are drugs, okay, that use as competitive inhibitors for HMG-CoA reductase. So that they design a drug that has a similar structure to HMG-CoA reductase. So these drugs, okay, statins, okay, have been used widely, okay, in medical to help to decrease the plasma cholesterol levels in patients of hypercholesterolemia. Okay, for those who have hypercholesterolemia, so you will get these statins. Okay, but it depends on the dose. Okay, either you need a very low dose or you need a very high dose. Okay, kalau high level ni, normally doctor will dia akan help you. Okay, the doctor will ask you to monitor your daily your lifestyle. Okay, your daily lifestyle, your diet intake, your daily activity, so that okay, it can help to reduce cholesterol levels. Okay, because it much related to your lifestyle. Okay. Okay, so for feedback inhibition, okay, so feedback inhibition basically it the enzyme can be inhibited by the intermediate itself, which is mevalonate and also cholesterol. Okay, so mevalonate and also cholesterol. So we know that mevalonate is the product, okay, the one of the intermediate in the cholesterol biosynthesis. Okay. Okay. So this one basically, this is the summary. So it tells us that this enzyme, okay, can be regulated through, okay, competitive inhibitors or hormones, okay, to the at the transcription level, how this cholesterol can block, okay, the transcription, okay, to stop the formation of HMG-CoA reductase. Okay, This one is the role of hormones, how hormones plays an important role in the regulation of cholesterol synthesis. So it involves insulin and glucagon, how this hormone involved in the regulation. So basically, phosphorylation, okay, decreases the activity of the reductase, which it catalyzed by the AMP-dependent kinase. Okay, and hormone glucagon, it favors the formation of the inactive form, which is phosphorylated form. So it helps to decrease the rate of cholesterol synthesis. In contrast, insulin favors the formation of the active form of HMG-CoA reductase. And this results in an increase in the rate of cholesterol synthesis. So you can see there is a much connection between insulin. Okay, we know that insulin helps to control the blood sugar, okay, but at the same time, it favors the formation of the active form of HMG-CoA reductase. So you can see how important, okay, the hormone, okay, in controlling, in regulating cholesterol synthesis. Okay, it also same goes to other pathways as well. Okay, there are other pathways that involve the role of hormone, okay, in regulation of certain pathway. Okay, so this is the diagram that shows on the activation of HMG-CoA reductase through to the phosphorylation, okay, that involve the role of hormone. Okay, so glucagon, it favors the formation of phosphorylated form. Okay, so phosphorylated form, okay, when reductase activity is inhibited by bile acids. Okay, it's inhibited by bile acids. Okay, fasting will also reduce the activity of HMG-CoA. Okay, okay, fasting is another, I think the important activity that helps to maintain your health. Okay, you don't, okay, Ramadan, okay, we are, okay, fasting is compulsory, okay, for Muslim. But other than bulan Ramadan, I think you can practice, okay, practice fasting Monday and Thursday, okay, so that it helps to, okay, either, okay, apart from reduce the activity of HMG-CoA, it helps to maintain the activity of our organs too. Okay, because our organs have been working so hard for the whole year, so that during Ramadan it can be, okay, it can be slowed down, it can recharge, okay, it can maintain, okay, the organs, okay, of our body. Okay, you can read the advantage of fasting, okay, to the organs, okay, to the activity of organs, okay, in our body. Okay, and also cholesterol synthesis, okay, so this is when the ATP level is low. Okay, all right, okay, another 5 minutes, you have class time. Okay, This one on the steroid-mediated regulation of transcription. I think this one is much related on the steroid-regulatory element binding protein. So it involves this SREBP. Okay. Okay, it involves the transcription of HMG-CoA reductase gene. Okay, so this one, I think I'm going to let's look at the gambar dalam. Sekejap Nope, I think I missed one of the photo. Okay, it's okay. I think I'm going to get back to you on this because I think I missed one diagram on this. I think it's much easier to explain on the diagram. Okay, because it involves the activation of this protein, steroid regulatory element binding protein, in the synthesis of reductase mRNA. Okay, how does this protein plays a role? Okay, in controlling the cholesterol level. Okay, so it's 4 o'clock. Okay, I'm going to continue on this on the bile acid synthesis mechanism next Friday. Okay, kita baca cepat sikit lah kot. Tak banyak sangat ni. Banyak juga. Okay, ada soalan? Do you have class after this?
Yes.
Yes, okay, all right. So I think we should stop here. So I'll see you again this Friday. All right, thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.